Thank you very much. So I'm going to be talking about optimizing our renderer for iOS and Metal. But before we go into the actual topics, I'm going to give a brief introduction into the company and myself. So Reforged Studios is a relatively young team. We're founded about 2 years ago by 4 industry veterans, like people who've been developing games such as League of Legends, World of Warcraft, Need for Speed, a long list of really high-profile titles. We're focusing on mobile games development, and we're situated in Helsinki, Finland. Personally, I started in the IT industry, did that for like 5 years, but I always wanted to be in the game development industry. That was kind of the reason why I got into like programming anyway. So I started doing some indie development on my own time while still in the IT industry. I had done a lot of like engine development hobby work before that, and I ended up using my engine for this project. Released one game on Android, but surprise, surprise, it wasn't really that much of a success. Had no experience about any business side of things, even though I knew how to make games. So I ended up moving to Bugbear Entertainment to finally get a job as a full-time game developer. Started working on racing games. That's what they do. Initially did some work on Ridge Racer Driftopia, which had a relatively short lifespan, sadly. But my main focus was on next car game Wreckfest, that I was also the lead programmer of towards the end of the project. After that, moved to Next Games to be the lead programmer on The Walking Dead No Man's Land, and helped out the Compass Point West team to ship that game as well. Then moved to Reforged Studios, where I'm now. So I'm responsible for maintaining the high-level vision and the architecture of our engine, and I like do most of the work on there because, well, we're a relatively small team. So now into the actual topics. What I'm going to start off with is a render architecture. So I'm going to give an overview of the architecture of our render to basically put everything into perspective. Then I'm going to be talking about tile-based rendering and Metal, so kind of giving an explanation on what tile-based rendering is and how we can use Metal to program on those platforms. Then I'm going to go through some of the tools and processes that we use in-house to optimize our engine. And finally, I have a list of like optimization tips and tricks, starting from like the big wins and moving on to the more detailed level shader optimizations. So let's start with the rendering architecture stuff then. So the Reforged engine is multi-layered. It has, like, each layer has its own optimization capabilities, of course. The lowest layer is architectured around Metal. So this allows us to take advantage of a lot of the architectural optimizations built into Metal on a higher level in the engine as well. And also, we put a lot of emphasis into writing lean and clean code. So this helps like existing engineers on the team to move between features and new people to like come into the team and start working on stuff. So there are like 3 major layers in our engine. The highest level layer is built on top of engine components or engine entity systems. And these are things, like very tangible things that you need for defining your scene, such as models, lights, and cameras. Then we have the middle-level renderer layer, which basically takes draw lists, a collection of draw commands that are pushed into the draw list and executed by the middle-level renderer. So the middle-level renderer then calls the lower-level APIs with that information. So the engine components are responsible for building these draw lists. The middle-level renderer can do a number of like different kinds of optimizations. One of the things it can do is that if you continue rendering into the same render targets, it can continue using the same render passes, which is very important in tile-based rendering, as we're going to see later in this presentation. We also have type draw lists, again, for ordering what types of geometry we render and when, and this is, again, very, very important. So the lowest layer interface, architecture around Metal, is very, very simple. It just has a number of simple interfaces for setting buffers, setting pipeline states, and doing the actual drawing. So this is used pretty much only by the mid-level renderer. We had like other layers of the engine use it before, but we moved that out because it makes it easier to group where the command buffers are actually generated. So rendering in our engine starts, of course, with allocating resources. Like we start the game, we need to load our textures, create our pipeline states, and whatnot. The first thing that we do at runtime is a shadow pass. And we do the shadow pass like, we use shadow mapping only for the really high-end devices. For the lower-end devices, we use shadow blobs. Then we render PBR linear lighting into a 16-bit floating point render target. So we have a fully linear PBR lighting pipeline. We do tone mapping on this and color correction as well. Render debug information, overlay that with UI, and finally, of course, clean up our mess when we change game states. So now onto tile-based rendering. How is it different from like basic stream-based rendering? So if you take the case of rendering a couple of triangles in a screen, what you do in a stream-based renderer, like simplified model of that, is that you just take the triangles, you take the vertices that compose that triangle, you process the geometry, rasterize, generate fragments, merge that into the frame buffer. In tile-based rendering, you split the screen into one or more small tiles. And you only process the geometry, or you use the geometry that really overlaps with these tiles. So you're able to like minimize the amount of data you need for rendering an individual tile. So what this means from a GPU architectural point of view is that the GPU, of course, is constructed like from multiple, or has multiple shader cores. These are organized in a SIMD manner. So each of the ALUs operate on the same instruction, but with different data. Very traditional model. But these are also typically 16-bit floating point optimized. So that means that it really makes sense to use 16-bit floating point math on these GPUs. It uses a lot less registry space because the registry file is split into 16-bit blocks on newer GPUs. And the logic is just so much simpler from a silicon point of view, so it uses a lot less energy and is typically just faster. Then you have a relatively small on-chip memory, which is what the shader cores want to use. So this is where we pull in all the data that, as much data as we can for that individual tile, so that we don't need to go into the system memory, do fetches there, because the connection between the system memory and the GPU is relatively low bandwidth because of energy consumption reasons. So that's why the architecture of tile-based renderers is built like this. The process of actually rendering something always starts with vertex processing. So for an individual pass that you're doing in a tile-based renderer, you need to know all the vertices that compose that pass. And you process that geometry. Then what you do is you perform tiling. So you determine which tiles will be affected by which geometry. And that's all that information is put into what's called a parameter buffer. So you have the process geometry, and then you have the list of tiles which define which geometry affects which tile. Then you perform rasterization, one tile at a time. Of course, you can have like multiple tiles in execution at any given time, but the idea is that you're processing one tile. And what's really important here is that in deferred rendering architectures, we also do hidden surface removal implicitly. So only the fragments that are the topmost are shaded when you're rendering opaque geometry. So that's why it's so important to render opaque geometry first, because it can do an implicit Z pass and use the Z value to determine if a fragment needs to be shaded. At the point you start rendering alpha-blended and alpha-tested geometry there, this all breaks. So then we do the shading on all the fragments, alpha testing, and of course alpha blending. So what is Metal then? Well, Metal is an API that is closer to Metal. So it's not as low level as Vulkan or DX12, but it's quite a lot lower than OpenGL ES. It's based on immutable states, so there's less runtime validation. All the validation happens at creation time of the states. And you get a lot more direct control and visibility into the pipeline. You get to control things like render surface load and stores. What happens to a render surface when you start rendering to that, and when you're finished with it? Do you need to store it? Resource allocation. You can do things like memory aliasing. You can use the same memory block for multiple textures. So one of the big benefits of Metal also is that it's updated with pretty much all the iOS updates. So iOS updates also tend to be available on older generation of hardware as well. So you can expect a lot of people to upgrade, and you get a lot of the optimizations over time for the older generation as well, because of the low barrier of entry. So the Metal command flow starts by acquiring a command buffer. So a command buffer is the construct that contains all the individual commands that are going to be executed on the GPU, and the queue is responsible for ordering the execution of these command buffers. Then the next thing you do is you acquire a drawable. And it's really important to acquire the drawable as late as possible, because the drawables, you have only a limited amount of drawables, and they will be locked as long as there are outstanding operations on the GPU targeting those drawables. Then you create your command encoder, which is responsible for encoding your draw calls. You use that encoder to encode your draw calls, and then you end encoding on the command encoder. The commands will not yet be sent to the GPU in stage 5. So now you can also register a command execution finish callback, which we're going to see is very important and very useful. And that is called when all the commands have been executed on the GPU. And finally, you commit the command buffer. So this is the time when the commands will actually be sent to the GPU. So Metal is not perfect. It has some rust spots. There's no dynamic extension mechanism, so using new features actually requires building against a new version of the platform. So supporting multiple platforms generally tends to become a preprocessor jungle because of all the different variations. Metal shader code is also a black box, so it's not possible to create tools that allow you to analyze that generated shader code in more detail. And there's a structure that I'm discussing about here later, which is function constants. That's a really cool feature, but it's not as powerful as preprocessor defines. And you do get information about errors happening on the GPU, but what you don't get is detailed information about what went wrong. So it sometimes makes troubleshooting a lot more difficult. Of course, it's also only on Apple platforms. A couple of words about Vulkan versus Metal then. Vulkan does have an extension mechanism, but it's a lot more complicated to use. So Metal kind of strikes a good point in between. It's a relatively easy API to use, but it has a bit less power. Vulkan gives you much lower access to resources and managing your resources. Oh, sorry. And then the shader, the system in itself is a lot more open because it's a standard, including the shading language, intermediate shading language used by it. So you can create a lot more tools for that. So Metal 2 was released in WWDC this year, and it contains a number of really cool features that are very important for optimizing. First of them, I'm going to be talking about that here soon, argument buffers. Let's leave the details for that. Setting resources in shaders. Raster order groups, that's very important for when you're doing things like custom blending. You're writing into resources. You can overlay your shader thread executions in a more finer-grained manner. But there is a divergence between OS X and iOS in some terms, like VR features, for instance. Multiple viewport rendering has only been added to OS X, which is kind of natural in case of this feature, but there are also others. Some features have been brought from iOS to OS X, which is also good, like the direct-to-display a very important feature that I'm actually be mentioning here in more detail. So yeah, and an improved tool set, that's a given. So argument buffers, the idea is that it allows you to embed resource references in your constant data. So this means that you don't have to individually bind all the, say, textures, for instance, for every draw call. It's just a lot more effective that way. All the data is still stored in constant buffers, as it was before, as it is with all the constant data. But you need to use a command or an argument buffer encoder to write your data into that buffer. And you get that encoder from a shader. So that can be, from an architectural point of view, that can sometimes be a bit challenging. Then during rendering, you just call use resource to tell the renderer that, OK, this is a resource that we're using for this pass. And there's support in 2 tiers. So I mentioned the setting resources on the GPU. That basically means changing the argument data on the GPU using a compute shader. That's not possible on iOS devices, for instance. iOS devices belong to tier 1, which is a more limited set of features. And then there's tier 2, which is like OS X, currently just like OS X. A lot of good tools. One of the most important here is GPU performance counters. So you get to see a lot more detail about what's happening on the GPU. Things like cache miss rates. You get to see when you hit your caches, when you miss them. Shader occupancy information. You get to know how well you're using your shader cores, etc. Basically, a really long list of individual counters. Also, finally, you have a render target pixel inspector, so you can actually compare the values in the render targets, like different layers of the render targets. And that's a feature that's been requested for a long time, and now it's finally available. Yeah, and I have links to other presentations from Apple talking in more detail about these new tools. So speaking of tools, I'm going to be now going through a couple of tools that we have used, some of the tools that have existed for a while, and some of the tools that we have built in-house as well for optimizing our engine. First of all, something we built in-house, which is deterministic profiling. So we have a regression testing system that allows us to spawn individual events at specific times or ticks. And the game code supports this by basically having all the game code implemented in a deterministic manner and using fixed point math. And also all the game events are scriptable. So we can execute any of those events at specific ticks and have a deterministic pipeline, a deterministic timeline that we can compare before and after making changes to code. Then we also have a pause feature. This allows us to pause the game at any time and just visualize how well we're performing for that frame. Also, we have an isolated static stress test scene. It's a very difficult set of words. This allows us to spawn individual animated models in a static scene and also spawn effects and freeze those effects at specific times. So we can create this really complex and expensive scene and basically look at what the performance statistics of that are before and after optimizing. So one of the tools that Apple provides that I've been using a lot is Metal System Trace. And this is a really good tool for looking at what happens on the GPU. So we have multiple lanes here. We have a lane that shows when command encoders are being used, when we're pushing commands into command buffers. Then we can see where the command encoder execution is currently at. So when vertex processing is happening and when that shifts into fragment processing. And also, we can see when the results of individual command buffer executions are being displayed. Then we have frame capture. This allows you to take a capture of an individual render frame and look at all the details in there. And here you have the frame events list or a tree which shows you which command buffers are being executed, which command buffers are taking part in that frame, and how well those command encoders are performing. So how long it takes to render an individual command encoder. And you can also open this up and see the individual statistics of individual draw calls and state changes. And of course, you have an overall of the performance, overall indicator. And then you can also visualize which vertex buffers have been bound, which shaders you're using, detailed information about them. Then you have a frame resources view where you can see which textures exist on the GPU at all, and all the texture resolutions and color formats and all that. And one of the most powerful features in here is the shader profiler. So this allows you to show how the performance of the shader is split over individual lines of code, as well as, what's really cool, you can change this code at any time. Just press this button, it'll re-render the frame, and you'll immediately see how your optimizations have affected the frame performance. So now let's move into the tips and tricks section. Let's start with the big wins, the ones that you get really the most benefit from. So the first really important thing is to minimize your passes. So passes have a relatively high overhead associated with them in tile-based rendering. You need to pull in your inputs for that pass, construct stuff like the parameter buffers and all that. And then you, of course, need to write out the results into system memory. So if you have multiple passes, you're jumping between system memory and tile local memory. Reducing passes have given us a huge benefit. Like, we had this case where we actually were erroneously creating a huge number of passes in UI rendering. We had, for individual UI batches, we were creating passes for every single batch. Removing those passes basically doubled our frame rate. And those were not expensive passes, so the overhead was huge. So there are two major ways for getting around this, for minimizing your passes. First of all, if you're just rendering into the same render target, you can just continue rendering. The more tricky part is when you need to do post-processing. And I have an example of how we're doing this next. So in a multi-pass PBR solution, you would render your scene into a floating point, 16-bit floating point render target, use that to do tone mapping, and then output a final BGRA color target. What we did here is we merged the render passes using programmable blending. So we bind two color targets, a 16-bit floating point color target into color 0, and a final drawable into color 1. Then we just first render the scene into color 0, and for tone mapping, we render a full screen quad, read from color 0, do the tone mapping, and just return the structure again with color 1 filled. So we never leave tile local memory, and we can do all of that in one pass. We got around 1.2 millisecond performance increase from this, which was relatively good for what we were already performing at. So triple buffering is also a really important topic. The reasons for this are that memory of graphics resources in unified memory architectures is shared between the CPU and the GPU. So you really need to be careful with synchronizing your memory accesses. Rendering is also performed one command buffer at a time. So that means that the command buffer will be locked for the duration of the execution of individual draw calls on the GPU, thus blocking the CPU if it wants to reuse that command buffer. And there's a latency between the communication of the CPU and the GPU. So how this is basically solved with triple buffering is that you allocate 3 command buffers, and then you allocate matching dynamic data buffers for that. So you push your constant data into these dynamic data buffers. And this basically hides wait times. Here's a schematic of how that works. So you start rendering using command buffer 0. you commit that, you're done with the frame. It takes some while for the GPU to start processing that. So you need another command buffer for preparing the next frame. Now you're done with the next frame on the CPU. You want to switch that for the GPU to start processing. But command buffer 0 might not actually yet be finished on the GPU, so you need a third one. But now when you're ready to commit the third one, you have probably already received the callback that your first command buffer has finished on the GPU, so you can reuse that. And it goes on and on and on. Another really important thing is direct-to-display. So direct-to-display, the reason why you need it is that desktop composition is usually done on the GPU. So the iOS drivers and iOS itself do composition of your frame, but full-screen applications generally do not need this. They render a full-screen image anyway, so we can skip this phase. But you don't skip that by flicking a switch. You actually fulfill a couple of boxes, or tick a couple of boxes to make that happen. So you only use opaque layers, you don't do any masking, any rounded corners, anything. You render full screen every time. You match your dimensions of your render target with the display, and you use a color format and pixel format that is compatible with the actual display. So those are the big wins. And now let's talk a bit about detailed shader optimization. One of the most important things on this side is to pay attention to registry usage. So the reason for this is that shader threads are dispatched in large groups, but the SIMD width defines how many of those threads can be in execution at any given time. The rest of the threads basically go for coffee at this point. The GPU then reschedules the execution of these threads whenever a thread block is blocked for some reason, like memory request, pending memory request. But the thing is that the contents of all of the individual registers of all of the threads needs to fit into the same registry file. So when you're using less registers, that means that you can fit a lot more threads to be waited, to wait for their time to execute. So you have a lot more filler threads, if you will. Using half-float math is a really good way of minimizing the amount of registers you're using, as already mentioned. For us, it gave like a 7 to 10% increase in performance just by using half-float math in our fragment shaders. Function constants are a really good way of removing code. They're really efficient for building Uber shaders. The idea is that you build your shader once, and then you just specialize it when you actually need the function. So you provide it with a couple of parameters to specialize it. We have, for instance, our materials have multiple specializations of these functions, like for depth-only rendering or for normal mapping versus no normal mapping and whatnot. You can use these constants in the same way as you would use any variable, any runtime evaluated variable or a constant. It means that if a block is not executed, it is actually removed from the code. It has no runtime performance implications whatsoever. But do note that you cannot change the input layouts of structures or layouts of structures that you use to access constant data using a command, using a function constant. One example that, for instance, we do is we limit the amount of bones affecting a single vertex using a function constant, and that's a per material property. You also need to pay a lot of attention to how you access your memory, how you address your memory, and what kind of data types you use for accessing memory. So the first thing you need to notice is to use the correct address space. So you should use the device address space for accessing device memory, that has you have a very large amount of that data, but you have very little reuse of that data. But you should use constant address space for data that you have relatively little of, but you are reusing a lot. So basically model constants like skinning matrices and light positions. And this is also interesting. When you're indexing device memory, you should use a value that has a range that is equal or smaller to a 32-bit signed integer. The reason for this is that a lot of modern GPUs have a special memory access instruction that takes a base 64-bit address and adds a signed 32-bit offset to that. But that needs to be a signed 32-bit. So if it cannot fit that value range, it'll need to manually compute the address, which is slower. Also, GPUs try to vectorize the reads. So if you have a structure with two fields that you're using in a loop, you should place those fields close to each other. One of the things that we, of course, constantly use when we're developing applications running on the CPU, like CPU code, is stack memory. But this is something you should never do on a GPU. So this can have potentially catastrophic costs. The reason for this is that GPU has a relatively small amount of memory, and a very small amount of that memory is allocated for stack. And you have a huge amount of threads that shares that memory. So what can result in this, for instance, is this kind of a case. You have dynamic values, and you're using a dynamic value to index that array. So this is what's called a dynamic stack array. And the GPU or the compiler has a very hard time figuring out what to actually do with this. So it might end up swapping back into system memory because it's running out of stack memory. And that's very, very bad. But do note, I'm using a function here, that GPUs generally do not support functions. So they're unrolled anyway. So it's fine to use functions however often you want. Then finally, I want to say a couple of words about texturing. First of all, use mipmaps and compression. The reason for this is cache efficiency. You have better cache efficiency overall. You use a lot less memory and a lot less bandwidth as well. Use half floats for sampling. So define your samplers so that they actually return half floats, because that allows you to minimize the amount of registers used for sampling textures. But don't spend a lot of time reorganizing your texture samples, because the GPU or the compiler does a really good job at that. So the caveat is that it cannot cross flow control or dynamic flow control. Of course, it can cross static flow control because the compiler can move the block out, but dynamic flow control, that's something you need to pay attention to. And finally, environment mapping. I wanted to mention this because we used cylindrical environment maps originally because we were using Substance Painter, which natively uses cylindrical environment maps, and we kind of ran with that. But then noticed that, oh, this is really expensive to actually use, so we switched to cube maps. And we use RGBA8 instead of 16-bit floating point to store HDR environment map data. This uses less memory and less bandwidth. The way we do this is that we use what's called an RGBM format, or a slight variation of that. So we scale the color values to range 0 and 1, but we select the maximum component, then we use that to scale the value. And we store the maximum component in the range 0 and 1 into the alpha component, so that in the shader we can actually restore an approximation of that color. Works really well for real-life cases where we have these really bright whites, but for cases like really bright red and some green, it basically crunches out the green. But that's not really a problem because the green wouldn't be that visible anyway. So that's pretty much it. there's a couple of references, really good slides from Apple at WWDCs for optimizing, for the different tools that they have. So I encourage you guys to look that up. And Imagination Block, that's a good resource for Power VR chip information. They go into a lot of detail about that. So I encourage you to check that out as well. Apple did announce, or they're using a new chip now on the iPhone 8 and iPhone X, which has a lot of really cool features. They have a couple of videos about that, so you can Google that up with Metal 2 videos, I think. Should find that. I didn't get that on this slide, so sorry about that, but should be easy to find. So yeah, that's it. I guess it's time for questions and answers.
Thank you very much.
Thanks.
Any questions?
Hi, thank you. My question about your slide about registers.
Yep.
How I can check how much my shaders takes SGPR or VGPR register or something else if, as you tell, shaders in metal is a black box? Can I profile assembler of shaders?
No, you can't really profile the assembly output or the intermediate language that it actually generates, the compiler. But now you have with Metal 2, you have the GPU profiler counters. So through that, you do get more information. But yes, it is in Metal, it is a bit challenging. In like other, like Vulkan, for instance, you can actually go into a lot of detail. So that is kind of one of the caveats of Metal. In general, because it's just a bit more closed.
Okay, so I am blind about registers, yes?
Partially, yes. You do get some hints, like, for instance, your occupancy. You can check your occupancy with the GPU profile, like counters in the frame, or for individual draw calls, actually. But you can't get that information from, say, your shader compiler output.
And another question about shader profiling. Can I debug shader step by step?
No, it's not really a sorry. It's not really a debugger. Oh. It's just for like checking the performance of your shaders.
And if I have a black pixel, I can only check my constant buffers. And just my lines of code.
You have a lot of like tools for that though. Like now you have the render target pixel inspector, so you can actually look at the individual values, compare the different layers that you're using, like your depth buffer and your like color targets and all that, and then your constant data, which is actually laid out pretty nicely nowadays. So yes, you do have to fill in the betweens, but they're constantly working on those tools, so it's getting constantly better, and I have like really high hopes for that. But yeah, sometimes you are a bit in the blind, and I've had to fight quite a lot with that, like over time.
Thank you.
No problem. Thanks.
Okay, thanks everyone. If you have any personal questions, you can catch up with Timo afterwards.
Yeah.
Thank you.
Thanks.
Hi, we're with one of our speakers who just gave his speech here. Please introduce yourself.
Hi, my name is Alex Shpilov. I'm head of gaming and esports at wiki.com. Hi.
Hi, nice to meet you. So tell us, what's your favorite video game?
Well, at this moment, my favorite game is Destiny 2. I have already spent a lot of hours in it, and it's really awesome.
It is, I gotta tell you. But this is a new game. What about the very first video game you've played? Do you remember it?
The first game was the first Quake. I played it with my dad in my childhood.
That's really great childhood memories, I guess. So tell me, how did you get to the gaming industry?
Well, I was a user of some fan community about Steam and Valve games, and I began to translate some games from some news articles and so on from English to Russian, and Valve invited me to translate their games as a volunteer, and after this I became such a dedicated employee at Valve, and now I'm here.
And what do you think about 4C?
It's my second 4C. I have already visited 4C in Kiev the last year, and it's really cool. I really love it.
Well, I hope you love this one as well, and I hope you get lots of new knowledge and share the knowledge as well. Did you have any questions from the audience that you really liked?
Yeah, the audience was cool. They asked really cool questions, and I hope my speech was really useful for them.
It definitely was. Thank you very much for your attention. Thank you. Hi, we've got one of our speakers again and wanted to ask him some questions. Hi, introduce yourself, please.
Hi, my name is Andrei Sarafanov. I'm a senior 3D artist from Wargaming. I'm working on World of Tanks project and creating 3D models of our tanks.
Fantastic. Andrew, tell me, what's the very first game that you've played? Do you remember it?
Actually, I think it was Tetris. Yes, I was amazed by the quality of the assets. I love to play this game all the time. But later, after I saw what computer games can do, I was I've tried to move to the PC gaming, and now I'm working on huge PC titles, and I love it.
Well, that's easy. Tetris had a fantastic destruction engine for its time.
Yeah.
But was it your favorite game, or which one is your favorite game of all time today?
Actually, today I like to play in our game Tanks, and Tetris was more like I had nothing to play, only Tetris. And today Tanks pretty much solves all my wishes, and all I want I can find in this game. It's kind of simple, pretty fast, not very long session, and I have a lot of time to work on my own projects. So that's why I like to play the World of Tanks.
Great. What led you to the gaming industry? How did you come to this industry, to this job?
Yeah, actually, I saw interesting CG Artist Challenge in the internet, and I saw cool character art from different artists all over the world, and I was amazed that young guys can create such amazing art. So I decided to try this out, and I found that it's not that hard, and I can learn that stuff. And I did it as in my spare time, just like a side project from my main job. And I was noticed by Wargaming at some point, and they invited me to join their team, and now I'm doing tanks.
That sounds like a great deal. So glad to have you in the industry. What's your favorite thing about it? Just about the game development?
Yeah, I like the diversity of this industry because it changes a lot and it has a lot of different branches all over the world, different people creating very interesting experience, and every year you need to adapt to the changes and learn new things. And it is very fast-moving industry, and I love it because you need to learn every day.
We definitely all love the industry, but there are maybe some frustrations, something that you don't like that makes you sad in the state of the gaming industry today?
Well, maybe some tools are not developed enough to meet our requirements, so we have to do too much technical work as an artist. But with every year, this issue resolves little by little. So I think it's pretty okay to work these days. So it's not a lot of problems, but a lot of fun.
I agree with you there. It definitely changes quickly. Where do you think the industry will be like in 10 years' time? Do you vision any trends?
As far as I can see, VR industry, it didn't have a good start, but it certainly takes pace. I saw a lot of good examples for artists, like software to paint in virtual reality. It works really well, and I think through the special software, VR will take its place, and at some point, most of game projects will go to VR in the future.
So you think it's going to be the next big thing for everyone, right?
Yes, of course, because it's really immersive experience, and you don't have any boundaries in VR when you use VR headset, and it slowly but surely takes its place, and I think we will be there.
Yeah, the immersion definitely improves with both VR and just the quality of graphics. But do you think the graphics are more important than the storyline, or the gameplay maybe is in the front, or a mixture of some of these?
You need to balance every aspect of your game. As an artist, I know that a lot of details are not that important. The more important the basic structure you want to show to the viewer, and you need to have like basic shapes which will be easy to read, and a narrative is a good example. If you have a good narrative, it can help you to support your characters and all your gameplay mechanics. So I think you need to balance every aspect of your game, and you will get achieve success.
Do you have any vision of a game that you'd like to create if you weren't restricted anyhow financially or creatively or professionally, just create anything?
Yeah, and I'm not sure about the genre, but in my spare time I want to create some universes. I'm doing it at the time, and maybe at some point I will make some game project from the assets I've created. So I'm working on it, but I'm not sure what will it be.
Well, whatever it may be, I hope it turns out well for you. But right now we're here in St. Pete. What do you think about the city?
It's my second time in the city, and weather this time is much better. And I love it because the architecture is amazing. Never saw anything like this before. And I love to visit museums. There is an artillery museum here, and I'm, as a tank artist, love to visit such exhibitions. I saw a lot of cool stuff, and we'll visit this city again in the future for sure.
It's great that you like it, but as far as I understand, 4C is one of the primary goals of your visit. What do you think about the event?
Yeah, event was. I didn't expect that so much speakers will come in one place, and I'm amazed by the quality of the organization structure so far. So far I love it. It's a very cool conference.
Do you have a favorite question that you were asked before the start of the conference yet?
Favorite question? No, I don't have.
What would you ask yourself then? If you were interviewing yourself, what would you like to open up with? What would you ask yourself?
Well, I don't know. It's kind of hard question for me.
It's fine, but it's kind of a retrospective thing. And any presentation that you're particularly looking forward to? Which one would you like to hear?
I've met a couple interesting people here, and I will attend their presentation for sure. But there are many of them, so I will not pick any one of them.
Well, I hope you get a favorite sometime along the line, and I hope you like the event overall. Thank you very much for your participation.